Hello everyone, thank you for coming. My name is Eric, and today I will present you our work titled Quadrupedal Locomotion Control on Inclined Surfaces using Collocation method. This research is funded by NSF Foundational Research in Robotics grant. This is a work in collaboration between Northeastern University, California Institute of Technology. We'll briefly introduce our collaborators and people working on this research. So we have our PI, Dr. Ramezani, which is a associate professor in Northeastern University. Dr. Miriam Lesser, which is a professor in Northeastern University as well. And our PhD students, Adas Alagame, Maria Janelo, Cheng Wong, Kaushik Venkatus Kritsamurti, Srians Priyatroda, and Rohit Hiraman Rajput, and myself, Eric Siete, which is from California Institute of Technology. So these slides will show some brief introduction of multimodal robots. So multimodal robots has multiple thrust actuators that can operate the robot in different modes of locomotion. So for example, we have ground aerial robots shown in this image. And these multimodal robots can operate over a wider range of terrains compared to single modal robots, and they can avoid obstacles by changing its mode of locomotion. For example, ground aerial robots can use its ground locomotion mode to efficiently traverse a relatively flat and obstacle-free terrain, or fly over obstacles to reach its destination. Some of these thrusters can complement each other. For example, for legged aerial robots like these two, Leonardo and Harpy, they can use the thruster to assist walking. There are some examples of state-of-the-art multimodal robots, such as M4 over here, which is a wheeled aerial vehicle that can transform between rover mode and UAV mode, and some other aerial robots, as I mentioned earlier, Leonardo and Harpy, which is a legged aerial robots. And there are some ornithopter wheeled robots like this one, MMLFE and Dash from Berkeley. There are other examples as well for different kind of multimodal locomotion robots, such as for amphibious robot that can swim and walk on the ground. This is an example of what we see in nature. So we call this wing assisted incline running, or WAIR. So we have an example of birds, flightless birds that can almost climb a vertical wall here using their wings to support them as they try to walk over this incline. So in this work, we aim to mimic this behavior using our thruster-assisted walking robot called Husky, which will be explained in the next slide. So here is Husky Carbon, as shown over here in the center. This Husky Carbon is a legged aerial multimodal robot developed in Northeastern University, and it's a quadruped with thruster attached on its spines. So it allows it to walk on the ground or uses thrusters to either hover or assist it in walking. Difficult to traverse terrains. The frame and legs, this guy, is composed of a lightweight carbon fiber and 3D printed materials to reduce most of the weight. The thrusters are composed of an electric ducted fans with a duct based on a carbon fiber lightweight frame. The robot weighs about 7.6 kilo and has a maximum thrust of 8 kilos, which is just enough to hover and lift the robot up. But in this work, we're going to use this thruster to assist walking in inclined surface to mimic the WAIR problem as shown earlier. So as mentioned earlier, in this work, we are looking to solve for a challenging WAIR problem using collocation method to allow Husky to climb a 45 degrees incline without violating the no-slip ground friction constraints. The robot legs trajectory are predetermined as shown over here. There's some potential leg positions that you can follow as it climbs the surface. And we're going to use some collocation method optimization to satisfy the ground friction constraints so that the foot does not slip. The collocation method will solve for a walking trajectory over a predetermined interval and enforce the constraints using optimization. So the collocation method will be applied on a reduced order model shown over here. We call this Husky reduced order model, or HROM. So it will be consist of just a single inertial body shown over here as yellow, and we have a massless legs showing as a prismatic legs with two joints, which is the frontal and sagittal joints shown over here. General form of this equation of motion will be this shown over here. So there's some mass inertia matrix, the states, some gravity and Coriolis matrix, and the sum of all forces acting on the leg foot end position, such as the ground forces, and the thruster wrench generated by the thruster on the body. In these slides, we show some brief derivation of the leg's kinematics. The leg is massless, so it follows a simple model shown here. It's modeled as a telescopic leg with two hip angle, hip frontal, and hip sagittal, and the leg length itself. So the foot position can be derived here, which is position of the body plus some rotation matrix of the length factors, and we can use this formulation to find the foot position, and also solving for the virtual work to apply forces to the main body to get the range on it. For the dynamics equation of motion, we simply follow a Lagrangian dynamics formulation shown over here. So we find the kinematic and potential energy of the system, which is just a single inertial body. And we use some modified Lagrangian for rotation in SO3 model over here. So the equation of motion will show some states in the rotation matrix form, and body frame angular velocity shown over here. So the states is done this way to avoid using Euler rotation. So we can avoid a singular rotation matrix using Euler angles. So we have a simplified form of this nonlinear equation of motion HROM, which is like a function of the states, and the three inputs, which is the leg acceleration, ground forces, and the thruster forces. This slide briefly shows the summary of the control design using collocation method. So cubic collocation is a Lobato point in a specific type of collocation method used in this work to find the optimal control actions for the WAIR maneuver. The Lobato points are set points of interval 0 to 1 that are commonly used in numerical integration and collocation methods. Cubic collocation refers to use cubic polynomials to approximate the solution between these Lobato points. So basically we have n intervals and we have to discretize that continuous equation shown earlier into some discrete points over here, and we have an optimization method to minimize this cost function given these constraints over here. So this is the dynamic equation constraint. So we have to follow x dot equal hf ROM over here. This is the ground friction constraint, which has to have the positive normal force and the friction force smaller than the static friction coefficient times the normal force. And R is the boundary conditions for this polynomial. So once we found the control points of this collocation methods, from this collocation method, we to implement that in the actual controller, we have the linear interpolation over here. Which will interpolate the steps in between these discretized points. To test the effectiveness of this controller, we implement it on a high-fidelity model shown over here on the right in Simscape multi-body environment. So Simscape multi-body runs on Simulink environment in MATLAB, and this high-fidelity model models all joints, components so that it's a full 80 degree of freedom model of the robot. So 6 on the body and 3 on each legs. So 12 plus 6 equal to 18. This URDF, this model is imported from the SolidWorks URDF. So it follows the actual design of the robot. The contact forces are generated using Simscape multimodal contact force library, which is shown over here as a flat surface and contact with this the foot of the robot to provide the force. So some simulation video of the robot climbing on the wall. There's no forces shown over here, but there are forces on the ground, and there are thruster forces applied over here at the thrusters itself. So As you can see, it can climb the inclined surface of 45 degrees just fine with the thruster assisted locomotion shown here. So this is the trajectory and of the legs and the friction force of the robot as shown over here in these two plots. So as you can see, like this is the inclined surface and this is the leg trajectory seen from the sides. So you can see like this is how it's the trajectory is followed by the robot. And over here we have the forces on various inclinations. So the friction constraint is shown over here on these lines here, but throughout all this simulation seems to follow strictly follows the friction constraint to avoid slipping. So as you can see over here. So in conclusions, we have demonstrated a thruster-assisted incline walking up to 45 degrees in high-fidelity simulation of Husky Carbon in the Simscape Simulink environment. And we have designed a collocation-based controller framework for solving this WAIR problem. And for the next steps, we have to implement this control framework on the actual robot and try to climb a similarly inclined surface as shown in the simulation. That is the end of the presentation. Thank you for listening and thank you for coming to our presentation. If you have any questions, you can contact our PI, which is Dr. Alireza Ramezani, shown over here as the contact person for these questions. Thank you.